So, welcome student to the new class of Introduction to Nonlinear Optics and its application. So, today we will have lecture number 31, and in today's class we will going to learn two important things. One is the realistic calculation of second harmonic generation, and then we will start the three wave interaction under second order effect. So, in the previous class, let me remind you, then the previous class we have started the second calculation of the second harmonic generation, and one of the major approximation that we have been taken, that during the second harmonic generation the fundamental wave, which is a frequency omega, is not changing throughout the distance. That means the fundamental wave remain constant. But this is not the realistic case. We know that when the second harmonic is generating, some of the energy from the fundamental wave is coming from that part to the second harmonic generation part. So, the second harmonic generation are a process where we have the energy exchange from the fundamental wave to the second harmonic wave. Since the energy is exchanged from fundamental wave to second harmonic wave, so what happened that physically the energy of the fundamental wave will going to reduce. So, we will going to take account these issues in our next calculation, and this calculation is realistic in nature, because this is the case one can expect in terms of energy conservation. So, that is why it is called the realistic calculation of second harmonic generation. So, let us start with this. So, in the previous class we have done few things. So, one important thing that we have derived, that one quantity is conserved over the distance, and that quantity is so let me go back to the slides. Yeah. So, one quantity is conserved, and that quantity is this one, the u1 square u2 multiplied by cos theta equal to 0. This is the term that was constant. So, this constant also we evaluated, that at u equal to z equal to 0 point, we know that u2 0 was 0. So, these things we used, and then we find that this quantity u1 square u2 cos theta, this constant is nothing but 0. From that we can find out what is the value of theta, as the equation suggests. So, the theta has to be the value of plus minus pi by 2, because u1 and u2 are changing throughout the distance. So, both of them are function of z. Cos theta is also changing. So, theta is a function of z, but theta is equal to phi 2 minus 2 phi 1, where phi 2 is the phase of second harmonic and phi 1 is the phase of the fundamental wave. So, they are related with phi 2 minus 2 phi 1, a parameter called theta, a single parameter. Now, theta is having a constant value pi by 2 throughout the distance. That is interesting. And now, if I put this value theta as pi by 2, then these two equation that is shown downstairs is delta u 1 delta z and delta u 2 delta z, which is the evolution of the amplitude of u 1 and u 2. These two can be written in terms of theta, and kappa u 1 u 2 sin theta and kappa u 1 square sin theta, these two are the set of equations. Now, if I put this value theta equal to pi by 2, then this equation can be simplified and can be represented at d u 1 dz is equal to minus kappa u 1 u 2, and also d u 2 is equal to dz kappa u 1 square. So, sin theta can be replaced by just 1, because we know that the theta is pi by 2. This is one condition. Also, in the future classes we see that we can take this pi by 2 as minus pi by 2, then the same equation will be there, only one negative sign in the first equation kappa u1 u2, this negative sign become a positive one and kappa u1 square become negative. So, that change will be there, and because of this change we will find that in one case we will get amplification, in other case we will get attenuation. That thing we will come later. So, now what we will do, that we will try to find out what is the phase equation, and the phase equation can also be one can derive, and this phase equation in the last class we have already derived, and in the phase equation if I put the condition theta equal to pi by 2, then we find that both the cases the phase del phi 1 del phi 2 remain conserved. So, the phases are not going to change throughout the distance. In this treatment, this is the thing we find. So, now our aim is here is to find out how the amplitude is going to change, which is rather important, that when the second harmonic is generating, that means there is 0 amplitude of second harmonic at z equal to 0 point, and gradually the amplitude will going to increase. So, we will going to find out how this amplitude is going to change over the distance when I consider the realistic situation. That means the fundamental wave is also changing, the amplitude of the fundamental wave is also changing. So, essentially what we will do, we will deal with these two equation here, and these two equation which is du 1 dz minus kappa u1 u2 and d u2 dz is equal to kappa u1 square. These two equation we will going to solve, and this is a coupled equation, to we will solve this coupled equation directly and try to find out how u1 and u2 will going to evolve over distance z, where u1 is the amplitude of the fundamental wave and u2 is the amplitude of the second harmonic wave that will going to generate because of this second under this second harmonic generation process. So, let me go back to our slides. Yeah. So, first let us try to find out how the energy conservation is here applied. So, first d u1 in the left hand side, if I see the calculation, d u1 dz is equal to minus kappa u1 u2 and d u2 dz is equal to kappa u1 square. These two equation is our mother equation. So, we will going to start from these two equation, and now if I try to find out what is the value of our total energy, then the total energy is proportional to u1 square and u2 square. So, now if I say that the total energy which is proportional to u1 square and u2 square, how this total energy is going to change, that means we need to take a derivative of u1 square or u2 square with respect to z. Once we take the derivative of u1 square and u2 square, we will going to find this equation 2 u1 d u1 dz plus 2 u2 d u2 dz. So, just making a derivative of u1 square and u2 square, and when you make this derivative we will simply get this form of equation. Now, what we will do, the coupled equation, the coupled equation is here, where u1 and u2 is coupled to each other, which is the two coupled equation for fundamental wave and second harmonic. So, what we will do, that we will just replace d u1 dz and d u2 dz to whatever the value we have here in our mother equation. Once we replace these two equation, these two value d u1 dz and d u2 dz, then readily we find one equation 2 u1 minus of kappa u1 u2, then plus 2 u2, and then if I replace d u2 dz, so d u2 dz is replaced by kappa u1 square. So, when I replace this thing, then we can see that these two things are cancelling out each other. So, 2 u1 square u2 with a negative sign multiplied by kappa, and then that should be equal to 2 u2 kappa and one additive term is there 2 u2 kappa u1 square. So, when we add these two terms, because of this negative sign, what we find that these two terms will be equal with opposite signs. So, they will going to cancel each other. Once they cancel each other, then readily we find out that d dz of u1 square and u2 square, this quantity is 0. So, u1 square u2 square, the derivative of this quantity is 0. That means that u1 square and u2 square are constant. So, they are not changing throughout the distance. So, that means the energy conservation is there. So, the energy is conserved. So, now another thing we should note that when I say u1 2 and u1 square and u2 square are conserved. So, that means u1 square u2 square that plus u2 square, that is a constant quantity. Now, if I put the boundary condition that what happened of this quantity at z equal to 0 point, then we find that u2 at z equal to 0 is 0, but this summation is conserved. So, that means u1 square u2 square which is at particular z point is equal to the u1 0 whole square or u0 square. That means, the total energy that was there at z equal to 0 point is equal to the energy distributed by u1 and u2, and that is why u1 square z plus u2 square z is u0 square. So, that means, the total energy is nothing but the energy that we have at the input, which is nothing but the total energy of the fundamental wave. So, at the input we have the total energy in terms of fundamental wave, and when the second harmonics are going to generate, it will take some energy from the fundamental wave. So, that the summation of these two energy remain conserved, and this constant value is nothing but the total energy that was incident at the input, that means at z equal to 0 point. Well, if I go to the next slide, we will now in this slide, this is an important slide, and we will going to find out what should be the value of u1 and u2. So, function u1 and u2 we will going to find as a function of z. So, now if I begin with d u2 dz, because my aim here is to find out u2. So, I need to solve this equation, and there is a tricky way to solve this equation, this coupled equation rather. So, kappa u1 square d u2 dz is equal to kappa u1 square, that we have in our previous slides. So, this is the equation we are going to use, this d u2 dz is kappa u1 square. So, that we know. So, now what we will do? We will use this equation here, and then u1 square 0 square minus u2 z, I replace these things, because obviously one kappa should be multiplied here. So, this quantity is equal to kappa multiplied here, the kappa is by mistake is not there. So, d u2 dz is equal to kappa u1 square, and u1 square plus u2 square z is equal to u1 0 square. So, I just replace u1 in terms of u2, and I will get this with a kappa value. And after having that, what we will do? We will going to integrate that. So, if I integrate, then d u2 divided by u0 square minus u2 square, 0 u2 is the limit, then that will be equal to 0 z and k dz, because in the right hand side we have k kappa dz. So, kappa dz will be integrated over, and we will have kappa z. In the left hand side, I can manipulate this term, I take u0 square common. So, 1 by u0 square will be here d u2, and then 1 plus u2 square divided by u0 square, that is the term we have. In the right hand side, kappa z as usual. Then I take u2 u0 as x. If I take u2 u0 as x, then d u2 become u0 dz. We replace this term here. When we replace this term here as dx, what happened? That 1 u0 will be here, and this 1 u0 divided by 1 u0 square will give you 1 divided by u 0. So, if I take 1 u 0 in the right hand side, it will multiply it with kappa z u 0. Once it is multiplied with kappa z u 0, in the left hand side simply becomes dz divided by 1 minus x square. Now, this is a standard integration, most of us can use the standard integration, but in sometimes we find that it is difficult to remember the standard integration, but one can derive it directly, because if I do this standard integration it become a log kind of thing, but you can directly put the value, or you can use the standard procedure. If I use the standard procedure, then 1 divided by 1 by x square can be represented by 1 by 1 plus x plus 1 by 1 minus x, is some sort of factorization. So, when I factorize, the half term has to be there, because here in the numerator 1 2 term will appear if I do that. In the right hand side we have kappa z u 0 as usual, this integration sign will not be there anyway. So, in the here we will have one equation, because when I integrate this part, we will have log these 2 I can put here. So, that I have 2 kappa z u 0. So, we will have the integration of this part is log of this quantity, and integration of this part is again log, and once it is going from 0 to x. So, that is why I can write it is log of 1 plus x divided by log of 1 minus x by putting the boundary conditions 0 to x, and then 1 plus x divided by 1 minus x in the right hand side, ln of that in the right hand side it is 2 kappa z u 0. So, it will become exponential 2 kappa z u 0. So, 1 plus x divided by 1 minus x is this quantity, and from that we can readily figure out what is my x. I just make a simple algebraic calculation, and when I make this algebraic calculation, this term becomes simply tan hyperbolic of u 0 kappa z. So, here is my goal is to find out what is u 2, but u 2 is represented in terms of x. I figure out what is x. X is nothing but u 2 divided by u 0. So, from here I can write that u 2 is nothing but u 0 multiplied by tan hyperbolic u 0 kappa z. So, u 2 z is now I find, if I consider the realistic calculation, I find that u 2 z is changing as a function of tan hyperbolic. So, it is interesting, because if you remember in the previous case, we consider that there is no pump depletion, that means u 1 is constant. So, in that condition, whatever the amplitude we figure out for second harmonic was proportional to z. That means, it is increasing linearly, and it is independent since it is increasing linearly. So, if I increase z, it will increase along z in a linear fashion. So, there is no saturation or something like that. So, that means, I am getting huge amount of energy, second harmonic energy, when I just increase my z value, and obviously that is not the correct case. We will show in the next slide by putting these two figures side by side. Obviously, that was not the correct calculation, because in that calculation we approximate a very and this approximation was that the fundamental wave is constant. So, it will not going to change, but fundamental wave is constant and still I am getting some kind of energy from the fundamental wave. This is the situation that can happen when the efficiency or the transfer of energy from the fundamental wave to the second harmonic is small. But if the amount of generation of second harmonic is high, or the efficiency of conversion of energy is very high, then we should not take this kind of approximation, and this is right now whatever the calculation we are doing, this is the correct approach to find out what is really the most realistic form. So, now the tan hyperbolic function suggests, if I now plot this tan hyperbolic function in terms of power, then this power is equal to tan hyperbolic square. So, the power of second harmonic will going to change as tan hyperbolic square, and here the green curve basically shows how the tan hyperbolic square curve will going to change. At z equal to 0, it is 0. That means, there is no second harmonic at z equal to 0 point, and if I go forward, if I go with increasing z, then what happened, that gradually the second harmonic will going to change and it will get some kind of energy, the amplitude will going to increase, this is in normalized form and reaches to a maxima and then saturates. That means, when the second harmonic is gaining the maximum energy out of the fundamental wave, so there is no way that it can change its amplitude, because the total energy is conserved. Since the total energy is conserved, it should be a saturation. There should be a saturation because the energy is conserved, and most of the energy I can take from or all the energy, in this case if there is no loss, I can assume that all the energy from the fundamental wave is now converted to the second harmonic wave, so that I will have a saturation at one point. That means, this is in normalized unit. So, all the energy is now transferred from here to here. Now, this is the energy thing for tan hyperbolic, when is what is the evolution of E2, but E1, the evolution of E1 is equally important. That means, how the fundamental wave will going to change, and here we can see that U1 square plus U2 square is U0 square, that is the equation for energy conservation. Once we have the energy conservation equation, I can write U1 is U0 square minus U2z square. U2z square is U0 tan hyperbolic. So, I can replace these things, taking U0 common, we have 1 minus tan hyperbolic square U0 kappa z. 1 minus tan hyperbolic square theta is nothing but sec hyperbolic square theta. So, I can just replace this as sec hyperbolic square U0 kappa z with U0 square as an amplitude. Then the power is proportional to this quantity, the power of 1, that means the power of fundamental wave, and the power of the second harmonic wave is proportional to the sine hyperbolic square, that we have already shown. In this plot we shows in this plot we have shown how this P1 and P2 will going to change as a function of z, and in one case when it is a second harmonic wave, we find that it will change as a tan hyperbolic square kind of function, and when it is the fundamental wave, it will reduce very rapidly and it will reduce in the form of sec hyperbolic square. So, now if I plot together, we find that this blue line, which is showing how the fundamental wave will going to decrease as a function of z, and as a result what happened, the energy is coming from this to this, and second harmonic wave is evolving, and it is evolving to a maxima and then saturates. So, this is the real picture, and in all the cases, all the times, if I see that at z equal to 0 point, all the energies are of fundamental wave. When I go to some z point, then I find that the total energy is now totally converted to second harmonic waves. So, all the energies are now going to second harmonic wave, and the fundamental wave, the energy of the fundamental wave is almost 0 or vanish. At each point, if I sum these two point, we will find that the sum will give you a constant value. For example, here 1 and 0 is there. So, if I sum this point, it is 1 plus 0. So, 1. At this point, both the cases it is 0.5 and 0.5. So, if I add, it will again give 1. So, this point and this point basically give me the addition of these 2 points are basically constant. That is the case basically we figure out for the total energy conservation, and this is in fact the total energy conservation condition. When if I add these two curves, then we will get a constant value, and in this case this constant value is 1. Well, after that we will side by side try to understand what is going on. In this is the old figure and this is the efficiency figure, old efficiency figure, and this old efficiency figure we show that how delta k equal to 0 case, this is changing very rapidly, and this change is a function of z square, and z is here in the x axis, and you can see that when k is not equal to 0, the efficiency is changing, but there is a sinusoidal change here, and efficiency reaches to a maximum and this then goes down. In this realistic approach, we can find that whatever the value we are getting at z k equal to 0 point, it is initially the structure is something like that. Here also it is increasing, and we will also getting here some kind of increment, but after that it is not saturating, but for realistic case we find that it is saturating to some point, which is rather more realistic. So, this approach suggests that the total energy remain conserved, but here this condition was not considered, because we consider the pulp there is no pump depletion, that means the energy of the fundamental wave is not changing, but here we consider that both are changing. So, that is why we get more realistic picture, and that is the correct one. Well, next we will going to see something about the 3 wave interaction. So far we are dealing with second harmonic generation, and in second harmonic generation what happened, that 2 wave, one fundamental wave is incident, and because of this fundamental wave we are getting a wave whose frequency is twice than the fundamental wave. So, that means if I launch omega, then 2 omega will merge and they will going to generate omega plus omega, but in 3 wave case what happened, that omega s and omega I, these two are there. When omega s and omega I are considered as signal and pump, now we put some kind of nomenclature that instead of having 2 wave we can say there is 3 wave, because omega 1 and omega 2 can combine to each other and generate omega 3. It may be omega 1 plus omega 2 or omega 1 minus omega 2. In one case it is a sum frequency and another is a difference frequency, but the thing is we will have 3 wave in our hand. So, now we will going to change the nomenclature and try to find out what happened for this 3 wave interaction. In the first case we can say that one wave we call pump, which is nothing but omega s plus omega I, that means omega signal and omega idler, these are the frequency of signal and idler. So, 3 waves are incident considered here, one is pump, one is signal and one is idler. So, in the input what we will do, that we will incident the signal all the cases. If with the signal we incident some kind of idler, and if omega p is equal to omega s plus omega I are valid, then we can generate a pump wave omega p, that is some sort of sum frequency generation. The same thing we are doing, but just change the name so that we can understand the process more clearly. But when we do the difference frequency generation, instead of launching idler we can launch a pump. Signal will always be launched at the input. So, omega s will always be in the input, only change we will change the idler or pump. So, when we change the pump idler to pump, then equation is same, omega p equal to omega s plus omega I, and omega I is generating. So, omega I is nothing but omega p minus omega s. So, this is nothing but the difference frequency generation. So, sum and difference frequency generation are there, but now we will going to understand what happened for these 3 wave, and this is called the 3 wave mixing. So, this 3 wave mixing we will learn in our next classes. So, today I think we should conclude here. So, in the conclusion I can say that we will in today's class we have learned 2 important things. One is for realistic calculation, what happened when the total electric field is conserved, and in total electric field, under the conservation of total electric field, the second harmonic are generated, and the second harmonic is generated at the same time the fundamental wave is also losing energy. So, that the total energy remain conserved, and from realistic calculation we see that it is really possible to find out how these things are increasing and decreasing. In one case we find it is increasing as a function of tan hyperbolic square, another case it is decreasing with the sec hyperbolic square kind of function. The differential equation, if I solve the differential equation, we are getting this. And in other case and finally, we find that the three-way mixing is something which we can also do in the next class. That so far we are dealing with sum and difference frequency generation, but today we will find that this sum and difference frequency generation, how we can do that using this new kind of nomenclature, namely pump, signal and idler. So, with this note I would like to conclude my class here. So, see you in the next class, and in the next class we will start this three-way mixing process in detail. So, thank you for your attention and see you in the next class.